There is one direction in the solar system that appears almost completely open, and that is up. The planets orbit the sun inside a thin, nearly flat disk. Above and below that disk, there are no planets blocking the path, no asteroid belt to cross, and no visible barrier of any kind. So flying straight up should be easy. Well, it is not. Every spacecraft launched from Earth already carries our planet's enormous sideways speed around the sun. To climb above the solar system, it must redirect that motion instead of simply adding more speed in the same direction. That turn can require more than 3 times the velocity change needed to escape the solar system outward. In over 60 years of spaceflight, only one mission has been built to make it. The obstacle is not what lies above us. It is the motion we already have. By the end of this video, you'll understand why flying straight up is one of the most expensive moves a spacecraft can make, why changing direction is harder than escaping the solar system, and how one probe used Jupiter to do what rockets alone could not. If you enjoy questions like this, take a second to like and subscribe. It really helps the channel. Now, let's begin. Wherever you are sitting, you know exactly which way is up. You feel it in the chair beneath you, in the weight of your feet against the floor, and in the quiet pressure settling every part of your body downward. You do not have to think about it. Close your eyes in a familiar room and you could still point toward the ceiling without hesitation. Every building you have entered was designed around that same direction. Floors below, ceilings above, staircases climbing one way, water falling in the other. It is an agreement so universal that nobody ever has to discuss it. The cause is Earth's gravity. It pulls everything toward the planet's center with such consistency that up and down stop feeling like consequences of physics. They begin to feel like permanent features of reality itself. You wake up tomorrow and the same floor will still be beneath you. The same weight will hold your body down. Entire cities are constructed around the assumption that this direction will never change. But that certainty does not travel with you. Leave the surface of Earth, and the meaning of up begins to disappear. Astronauts aboard the International Space Station live with no physically meaningful ceiling or floor. The interior is arranged to give the crew a shared orientation, but that layout is chosen for convenience. Another crew could decide that a different wall was the floor and function just as well. Some surfaces are painted or labeled to suggest which way everyone should face, giving the brain something familiar to hold onto. But gravity does not enforce that choice. Flip the entire station upside down relative to Earth, and nothing changes for the people inside. No falling sensation, no correction, nothing at all. A wrench released in midair does not drop toward any particular wall. It simply stays where it was let go, drifting, waiting for a hand to come back for it. Here's the strange part. The station is not free of gravity. Earth's gravity still reaches it, still pulls on it, almost as strongly as it pulls on you sitting there right now. The reason astronauts float is not an absence of gravity. It is that the station never stops falling. The station is in permanent free fall toward Earth. It is dropping, constantly, the same way anything dropped from a height drops. But it is also moving sideways at several miles a second, fast enough that the curve of the planet falls away beneath it just as quickly as it falls toward it. It keeps missing the ground, fall, curve, miss, fall, curve, miss, over and over, forever failing to reach the planet. It is always falling toward. That endless missing is what an orbit actually is. Not an absence of gravity, but a very long, very graceful fall that never lands. Free fall removes weight completely. And without weight, up and down stop meaning anything to the human body. The adjustment is not instant, and it is not always comfortable. Astronauts describe real disorientation in their first days aboard the station. The mind hunting for a flaw that simply isn't there. some reaching for handholds that a body on Earth would never need. Most settle on the module's visual layout as a stand-in, ceiling-coloured surfaces treated as up, floor-coloured surfaces treated as down, a kind of agreed fiction the brain accepts because it needs something to accept. But drift into a module oriented differently, and that sense of up can flip completely. Sometimes within seconds, the whole body suddenly certain the wall is now the floor, and the floor was the wall all along. That flip is the clue worth holding on to. It shows that up and down were never properties of space itself. They were always properties of gravity, specifically the gravity of whichever large mass happens to be nearby. On Earth, up points away from Earth. Near the Moon, up points away from the Moon. Near Jupiter, up points away from Jupiter. Change the nearest mass, and the direction changes with it, instantly, without asking your permission. There is no universal upstitched into the fabric of space itself. No cosmic ceiling, no cosmic floor, no direction that space itself prefers over any other. Not a fixed direction, a local one. Not built into the universe the way a law of physics is built into it. Borrowed instead from whatever mass happens to be closest and strongest, for exactly as long as you stay near it, and handed back the moment you leave. Every up you have ever trusted, the floor under this room, the ceiling over your head, was a loan from Earth, not a gift from the universe. That changes the question this whole exploration is built on. If up isn't a fixed direction, if it dissolves the moment you leave Earth's gravity behind, then what does it actually mean to go up out of the solar system? Up according to what center? Away from what plane, what mass, what shared motion? The question sounds simple until you notice it has no fixed target to aim at, and answering it means starting over from the beginning. Answering it means setting the human body aside for a moment and looking outward at the actual shape of the solar system itself, stretched across billions of miles around the sun. It is not the shape most people picture. It is flatter and stranger than almost anyone assumes. And that flatness is where the real cost of up begins. Picture the solar system the way most diagrams draw it. A sun sitting at the center, planets scattered loosely around it in every direction, some higher, some lower, drifting the way marbles might settle if you tossed a handful into a dark room and let gravity pull each one down wherever it landed. It looks like a sphere. It looks random. It looks like the sun could have planets circling it from any angle at all, above, below, sideways, anywhere. That picture is wrong. The real solar system is almost perfectly flat. Every major planet, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, circles the sun in nearly the same plane, tilted away from one another by only a few degrees at most. Not scattered, not random, lined up. The tilts are small enough to count on one hand. Mercury leans about 7 degrees from the shared plane, the largest wobble of any major planet, roughly the pitch of a gently sloped roof, and even that barely counts as a tilt against the size of the whole system. Venus leans about 3.4 degrees, Mars about 1.8 degrees. Jupiter, Saturn, Uranus, and Neptune, planets hundreds of times more massive than Earth, all sit within 1 or 2 degrees of the same line. Bodies large enough to swallow Earth whole several times over, holding almost exactly the same course as the rest. Shrink the whole solar system down to the size of a dinner plate, sun at the center, planets riding along near its rim, and you would struggle to tell it apart from a single flat sheet resting on a table. Not a bowl, not a ball, a sheet, with the sun at the middle and 8 planets tracing its surface, none of them straying far enough to lift the picture off the table. Earth's own orbit gives astronomers the reference line this entire shape gets measured against. They call it the ecliptic, simply the flat path Earth traces around the sun, extended outward as the ruler everything else in the system is compared to. Ask where Mars sits relative to Jupiter, or how steep a comet's path runs, and the answer always comes back measured against that same line. Why Earth's path specifically? Mostly convenience. We live here, we measure from here, and Earth's own tilt happens to sit close enough to the system's overall average that the line barely needs correcting. But the flatness runs deeper than one planet's path. It has a second name, the invariable plane, defined not by Earth alone, but by the combined spin of the whole system. Every planet, every moon, every significant chunk of rock and ice weighted together into a single average direction of rotation. Think of it as the system's center of balance, the one axis the whole spinning arrangement leans around. That plane barely moves, even across millions of years. It is the deep rotational memory of whatever the entire system was built from. A memory none of the planets could shake off, even if something tried to knock them loose. And here is where it gets strange. This shared plane is not a coincidence, and it was not arranged by anything watching over the system. Not an accident. A consequence. The reason every planet holds the same line traces back to how the whole system came together in the first place, long before any planet existed to hold a line at all. That story, the collapse, the spin, the flattening, is still ahead of us. For now, hold onto the pattern, because it does not stop at the planets. The asteroid belt, that scattered field of rock and rubble sitting between Mars and Jupiter, keeps close to the same plane, drifting through the same flat band the planets occupy rather than scattered above and below it. Millions of fragments, some no bigger than a pebble, some hundreds of miles across, and nearly all of them tracing the same shared line the planets trace. The Kuiper Belt, the icy debris ring far beyond Neptune, holds close to it too, at least in its calmer, more settled regions, the ones that formed early and never got knocked loose. Even the rings circling Saturn, Jupiter, Uranus, and Neptune, vast bands of ice and dust that could each swallow a planet's shadow, lie flat against each planet's own equator, and each of those equators lines up roughly with the shared plane of the whole system. Look closely enough at any one planet's rings, and you are looking at a miniature version of the same disk the whole solar system forms, a flat sheet repeating itself at a smaller scale, tucked inside the larger one. A planet, a belt, a ring. Look at any scale you choose, the largest worlds or the smallest scattered debris, and the system keeps returning to the same flat shape, the same shared direction of motion, set once at the very beginning, with nothing powerful enough since to shake it loose. So, up inside this solar system finally has a precise meaning. Not away from the sun, not toward any particular star. Up means perpendicular to the disk, straight above it or straight below it, away from every planet, moon, asteroid, and comet, lined up along the one flat plane they all share. It sounds like a small correction to a childhood picture. It is not. Every mission this piece is about to follow, every fuel calculation, every reason up, turns out to be one of the hardest directions in the solar system to travel, rests on this one flat fact. A cloud of planets scattered in every direction would make up meaningless. Just one direction among infinite others. No more special than any other. A disk gives up a shape, a target, and eventually a cost. Hold that image for a moment. A sun at the center. 8 planets tracing one shared plane around it. A scattering of rock and ice, belts and rings, all leaning on the same flat surface, none of them straying far enough to break the pattern. It is a strangely tidy arrangement for something built out of chaos. A swirling cloud with no reason to organize itself so neatly. And yet, here it is, billions of miles across, still holding the same flat line it settled into long before Earth had an ocean or a sky. And a flat disk this precise holding steady across billions of miles and billions of years, did not arrive that way by chance. Something forged it. Something old enough to have shaped the sun itself before the sun had finished becoming the sun. And that something is where the story has to go next. The year was roughly 4.5 billion years ago. Before there was a sun, before there were planets, there was only a cloud. A single, roughly spherical cloud of gas and dust, drifting through space with no particular flatness to it at all, rotating slowly, almost lazily, in whatever direction it happened to be rotating. That cloud had one property it could not lose: angular momentum, the physical measure of how much spin a thing carries. And spin does not simply disappear, it has to go somewhere. Gravity began pulling the cloud inward, and as it collapsed, the rotation did not fade. It concentrated. Think of a figure skater pulling their arms in during a spin. The same amount of spin, packed into a smaller body, comes out faster. The cloud did the same thing on a scale no skater ever could, shrinking and spinning faster with every stage of its own collapse. But faster spin alone does not explain a disk. Spin a sphere faster and you still just get a smaller, faster sphere. Something else had to happen, and it happened through collisions. Inside that collapsing cloud, particles of gas and dust were moving in every direction at once, above the eventual plane, below it, sideways through it, colliding constantly. Every collision was a small negotiation. Motion that lined up with the overall spin of the cloud reinforced itself, particle pushing particle in the same general direction. Motion that ran perpendicular to that spin had nothing reinforcing it, and collision by collision, it was cancelled, its energy bled off as heat and radiated into space. No single collision mattered much on its own. Multiply it across countless particles over thousands of years, and the pattern became unavoidable. Sideways motion survived. Vertical motion did not. Over that stretch of time, that constant grinding damping did what raw spin alone never could. It ironed the cloud flat, the way a handful of loose sand thrown into a spinning bowl settles, no matter how randomly it started, into one thin, even layer. Not designed, not arranged from above. A consequence, worked out one collision at a time. What was left was a thin, spinning disk, dense enough at its center to collapse further and ignite as the sun, with smaller clumps scattered through the rest of it, slowly gathering into planets. Those planets never chose their shared plane. They condensed out of material that was already flat before a single planet existed to have an opinion about it, inheriting the disk's orientation the way a child inherits the shape of their handwriting, copying a motion they never consciously picked. And the small differences between the planets, the tiny wobbles in their tilts, are not noise. They are history, still readable billions of years later. Mercury's tilt, the largest of any major planet, is thought to be a leftover scar from the chaotic, crowded environment closest to the sun, where fewer neighboring bodies were around to smooth its path, and where the sun's own gravity was strong enough to stir up trouble. The damping never fully settled. Jupiter and Saturn, by contrast, lean less than 2 degrees from the shared plane, remarkably flat for planets that could each swallow Earth many times over, likely because they gathered their mass from the smoothest, most thoroughly settled part of the disk, farther from the sun's disruptive pull, the part where the collisional damping had already finished its work, before those planets ever began pulling gas toward themselves. So far, the pattern holds, but it does not hold forever. Move out past Neptune, and the tidy picture starts to fray. Pluto, no longer counted among the major planets, orbits at an incline of about 17 degrees, the steepest of any well-known body in its neighborhood, a sign that something disrupted its path, most likely a long gravitational tug-of-war with Neptune itself. The kind of nudging that never fully evens out the way it did closer to the sun, where more material and more collisions meant more chances to smooth things over. Push farther out into the Kuiper belt, and the tilts only grow more scattered. Eris, a dwarf planet discovered in 2005, spends much of its long, stretched orbit tilted nearly 44 degrees from the plane, swinging well above it and well below it in turn. Sedna, one of the most distant and slowest moving objects ever tracked, holds a comparatively modest tilt of about 12 degrees, but it travels so enormously far from the sun that even that small angle carries it an immense distance off the flat line the inner planets never leave. Distance, it turns out, forgives nothing. The farther a body sits from the sun, the less chance it ever had of being pulled into line. The order is fraying, and it does not stop fraying. Beyond even the Kuiper belt lies the most distant region still gravitationally bound to the sun at all, the Oort cloud. Here the disk does not just weaken, it disappears. Not flat, not a disk at all. A shell wrapped around the entire solar system in every direction equally. The Oort cloud is believed to hold its icy bodies in a roughly spherical arrangement, unlike the flat, orderly Kuiper belt closer in. No spacecraft has ever reached it. No telescope has ever imaged it directly. We don't know its shape the way we know the shape of the asteroid belt or the rings around Saturn. Its existence is inferred, not observed, pieced together mainly from long-period comets. The ones that take centuries or longer to loop back toward the sun and fall in from directions that look essentially random rather than clustering near the ecliptic, the way short-period comets do. The ones that still orbit close to the flat plane and betray a Kuiper belt origin. That randomness is the clue. A flat structure sends its debris in from a favored direction. A spherical one does not favor any direction at all. It may stretch somewhere between 5,000 and 100,000 astronomical units out from the sun, a span so vast that the 8 planets, huddled together near the center, occupy only the tiniest fraction of it. Most of that material was likely flung outward from the flat inner disk billions of years ago, kicked loose by gravitational encounters with the giant planets, and scattered so thoroughly that any trace of its original flat shape was erased along the way. Here is the contrast the whole shape depends on. Close to the sun, where gravity is strong and collisions were constant, billions of years of settling produce something close to perfect flatness. Far enough out where those same encounters are rare instead of relentless, that settling never finished, or was undone entirely. And where the settling stops, so does the meaning of the word up. Out at the edge of the Oort cloud, there is no plane left to be perpendicular to. There is only a shell, equally full and equally empty in every direction at once. Come back from that shell now. Back through the scattered tilts of the Kuiper belt. Back through the tidy planets riding their shared plane. Back to the sun at the center of it all. The question that started this has a shape now. A real one, not a vague gesture at the sky. Up, out of the solar system, means one specific thing. It means moving perpendicular to the disk, straight above it or straight below it, away from the plane where the planets ride, where the moons trail their planets, where the asteroids drift and the comets loop home on their long orbits. Not outward along the disk, the way every planet and every probe sent so far already travels. Up and away from the disk entirely, off the flat sheet the whole system rides on. Said plainly like that, it sounds almost easy. There is no planet sitting in the way. No belt of rubble to dodge, no wall of debris, no boundary marked "do not enter." The space above the disk and the space below it are exactly as empty as the space inside it, mile for mile, and just as empty as the space a probe crosses heading straight out toward interstellar space. A spacecraft aimed at the sun's north pole tomorrow would not hit anything. A spacecraft aimed outward along the plane would not also risk. nothing physically blocks the direction. Nothing waits up there to be avoided. You could point a rocket at that empty space above the ecliptic, and nothing in the geometry of the solar system would stop it from arriving. So why hasn't it happened? Why, in an era of spacecraft that have landed on comets, driven across another planet's dust, and photographed the icy edge of the solar system up close, has almost nothing gone the one way that offers no obstacle at all? What could possibly make an empty, unobstructed direction the hardest one to choose? And yet, in more than 60 years of launching spacecraft off this planet, longer than most people watching this have been alive, humanity has built exactly one mission whose entire purpose was to leave that plane and travel over the sun's poles. One, out of every probe sent to a planet, every lander set down on a moon, every flyby threaded past a ring system, every rover that has ever driven across another world's dust, every spacecraft now crossing the outer dark on its way out of the solar system for good. All of them, without exception, have stayed remarkably close to the same flat disk. Decades of launches, dozens of destinations, entire careers spent planning trajectories, and only a single mission in all of that ever aimed itself away from the plane on purpose. That is not a small fact. That is the whole shape of the mystery, compressed into one number. One mission against every other mission ever flown. It is not for lack of interest. Scientists have wanted a clear look over the sun's poles for as long as there have been scientists studying the sun. Its magnetic field twisting and flipping in ways nobody has ever watched from directly above. The way you might finally understand a spinning top by looking straight down its axis instead of from the side. It is not for lack of imagination either. Nobody ran out of ideas for where else to aim a spacecraft. Something else kept every other mission tethered to the plane. Something with nothing to do with curiosity and everything to do with what a rocket can actually afford to pay for. Not blocked, not forbidden, simply never paid for 60 years running. 60 years is not a short stretch to come up empty. In that same span, spacecraft have visited every planet in this solar system, several of them more than once. They have orbited moons, skimmed the tops of gas giant clouds, and drifted past the edge of everything the sun holds onto, out into true interstellar space. Every one of those missions solved problems that once looked impossible. And still, only one of them ever pointed itself straight up out of the plane on purpose. Whatever stands in that direction's way, it is not a problem engineers forgot to consider. It is a problem they looked at closely, for decades, and could not make disappear. The reason is physics, and it is brutal. That one mission exists, and it earns its full telling soon. The planet it borrowed from, the strange two-step path it had to take just to get anywhere near the sun's poles at all. It is the answer to the question this section just raised, and it deserves more room than a passing mention. For now, it is enough to know it is out there, waiting a little further along in the story, the single exception standing against 60 years of everything else staying flat. But before that mission's story can make sense, there is a harder question sitting underneath it. Why should straight up, through completely empty space, be the one direction almost nothing has ever gone? Not because anything stands in the way, because of something every spacecraft carries with it before it ever clears the launch tower. A debt built into its own motion from the moment it left Earth. One that has nothing to do with distance and everything to do with speed. It was never asked whether it wanted. That debt is where the real explanation begins. And it turns out to be stranger and far more expensive than the empty space above the plane ever let on. The debt is not a metaphor. It is speed, carried by the spacecraft before the rocket ever clears the tower, spent before the mission has properly begun. Earth is not standing still. It sweeps around the sun at an average of about 18.5 kilometers a second, more than 66,000 miles an hour, carried sideways through the same flat plane every other planet rides. A rocket does not launch from zero. It launches from a planet already moving that fast, and the instant the spacecraft clears the atmosphere, it still carries Earth's full sideways rush around the Sun, whether the mission wanted that speed or not. For a mission staying in the plane, that inherited rush is a gift worth building on. Point a spacecraft outward in the same direction Earth is already flying, and the planet's own motion becomes a running start. Free speed toward the outer solar system that no engine had to supply. Mission planners lean on it every time, launching with Earth's motion instead of against it. The same way a ball thrown forward from a moving train carries the train's speed along with whatever push your arm adds. Nobody pays for that speed twice. It is already there, waiting to be used, and every outward bound mission in history has used it. For a mission trying to leave the plane, the same rush turns hostile. Going up out of the ecliptic is not simply a matter of adding an upward push on top of what the spacecraft already has. The sideways speed has to be cancelled first, the whole inherited motion undone before any climb above or below the plane can even begin to show. Think about it this way. Stand on a merry-go-round spinning at full speed and try to walk straight off the edge, directly away from the center, none of the circular motion carried with you. It cannot be done by simply stepping off. Your body is already moving in a circle, so you fly off at an angle, carrying that sideways momentum along whether you want it or not, unless you cancel the spin first. A spacecraft leaving the ecliptic faces the same problem, except the merry-go-round is the entire solar system, and the spin is 18.5 kilometers a second of sideways velocity that has to be cancelled before any real upward motion can dominate the path. Engineers put a number on this cost. They call it delta V, the total change in velocity a spacecraft's engines have to supply across an entire mission. Every gram of fuel buys a little more delta V, and every maneuver spends some of it back down. It is the currency the whole enterprise runs on. And like any currency, some purchases cost far more than they look like they should. Think of delta V as a fixed budget loaded onto the spacecraft before launch, sealed inside the fuel tanks and never topped up again. Spend it correcting course, spend it slowing down to enter orbit, spend it speeding up to leave one behind. Once it is gone, the mission flies on whatever velocity it already has, forever. Every maneuver a planet ever designs starts with the same question. What does this cost in that one sealed budget, and is there enough left to pay it? Here is what that currency actually buys. Escaping the sun's gravity outright from Earth's orbit requires a velocity of about 26.4 kilometers a second relative to the sun. The spacecraft already carries 18.5 of that for free, inherited at launch, so engineers only have to add roughly 7.9 kilometers a second in a useful direction. Large, but achievable. Voyager and New Horizons both did it, with powerful rockets and a few borrowed nudges from planetary gravity along the way. Leaving the plane is a different kind of expensive. Cancel the inherited 18.5 first. Then build fresh velocity straight up, out of the ecliptic. A direct 90-degree turn at Earth's orbital speed can cost somewhere around 26 kilometers a second of delta V, done all at once. Wait, look at those two numbers side by side. Escaping the solar system outward costs about 7.9. Turning 90 degrees out of the plane costs about 26. The turn costs more than 3 times what the entire escape costs. That is not the order most people would guess. Crossing the whole solar system and leaving it behind for good ought to cost more than simply pivoting to face a new direction while staying close to home. In orbital mechanics, it runs the other way. Changing direction while moving fast is often more expensive than changing speed by that same amount, because a turn does not add motion on top of what is already there. It has to cancel a large existing motion and build a new one from scratch, and both draws pull from the same limited tank of fuel. Say it again, plainly, because the whole rest of this story leans on it. Adding 7.9 kilometers a second in the direction you are already flying gets you clear of the sun forever. Turning through 90 degrees at 18.5 kilometers a second costs about 26. Same starting speed, same spacecraft. One path costs a third of the other. 26 kilometers a second is a brutal number to put on paper. A rifle bullet leaves the barrel at something like half a mile a second. A direct plane change asks a spacecraft to shed speed and rebuild it at more than 30 times that rate in the empty stretch above or below the ecliptic where nothing has ever stood in the way. No chemical rocket ever built carries anywhere near enough propellant to deliver that much change directly. Not and still arrive with anything left over to do useful science. Chemical propulsion, the kind that has powered every crewed and uncrewed mission ever flown, simply does not carry that much fuel. Load a rocket with enough propellant to spend 26 kilometers a second in one motion, and there is no room left for the spacecraft, the instruments, or anything the mission was built to learn. Nothing seriously proposed with current technology carries it either. No wall stands above the plane, no fence, no debris field, nothing to dodge, only a price, and the price is steeper than the price of leaving the sun's grip entirely. This is the rule the rest of the story keeps returning to. The cost of changing direction scales with how fast you are already moving, so the faster the inherited motion, the more brutal the turn. Near Earth, moving at 18.5 kilometers a second, that turn is close to the most expensive maneuver anywhere in orbital mechanics. It costs more than leaving the solar system altogether. That is the debt hiding underneath the empty space above the disk. Every spacecraft is born already spending, carrying a speed nobody asked whether it wanted, and shedding that speed turns out to cost more than escaping the sun's pull ever did. Brute force will not pay this bill. But a bill this large does not mean the door is closed. It means the direct route is closed. Somewhere between an impossible maneuver and an abandoned idea, there is a third option, and it does not fight the 26 kilometers a second head-on. It goes looking for a cheaper place to spend it. One mission found that cheaper place, and it did not pay in a straight line. That mission was Ulysses, a joint project of NASA and the European Space Agency, launched in October 1990 from the Space Shuttle Discovery. Its job was unlike anything flown before or since. Fly over the sun's poles, above and below the ecliptic, and look at the solar wind and the sun's magnetic field from an angle no instrument had ever managed. Every mission before it, every telescope and probe ever pointed at the sun, had studied it from within a few degrees of the same flat plane. Ulysses was built to look from above, not a bigger telescope, not a closer approach. A different angle entirely, one nothing in the solar system's own layout had ever handed to a spacecraft for free. Engineers ran straight into the same wall the last section put a number on. No rocket existed that could cancel 18.5 kilometers a second of inherited sideways motion directly and still deliver a working spacecraft anywhere useful. 26 kilometers a second, spent all at once, was simply not on the table, not with chemical propulsion, not with anything close to it. So they did not fight the bill head on. They looked for a cheaper way to pay it, and borrowed a gravity assist in a way nobody had used one before. Ulysses launched toward Jupiter, not to study Jupiter, to use it. On its approach in February 1992, Jupiter's gravity bent the spacecraft's path in a way most gravity assists never attempt. Most assists nudge a spacecraft sideways or speed it up, still inside the plane, still riding the same flat disk every planet shares. This one did neither. Not sideways, not faster. Bent straight up, out of the ecliptic entirely, onto a path that would carry Ulysses far above the sun's north pole, and years later, far below its south pole. Not a full 90 degrees. Close. At its steepest, Ulysses reached a maximum ecliptic latitude, a little over 80 degrees, tilted almost far enough to look straight down the sun's axis instead of across it. Short of true vertical by the last stubborn 10 degrees, Jupiter's geometry could not quite supply. It crossed over the poles more than once, running years past its planned lifetime, sending data back until it was finally decommissioned in 2009. No other spacecraft, before or since, has flown a mission built entirely around leaving the plane. Reaching Jupiter at all took years. Ulysses did not climb toward the poles. The moment it cleared Earth's gravity, it spent a long, patient stretch simply crossing the distance outward first, coasting through the same flat plane every other outbound mission uses, waiting for the one encounter that would bend its path somewhere no rocket could push it directly. The years were not a delay before the real mission started. They were the first half of the maneuver, quietly banking the setup for a turn that would only pay off once Jupiter's gravity was close enough to use. It is tempting to read that as Ulysses breaking the rule the last section laid out. It did not. It proved it. The only way out of the plane was borrowed, not built, and it still took years of outward travel before the real maneuver could even begin. But here's where it gets strange. A gravity assist can look like free speed, conjured from nothing. It is not. As a spacecraft falls toward a planet like Jupiter, gravity curves its path, speeding it up on the way in and slowing it down by the same amount on the way out. So relative to the planet itself, nothing is gained. Relative to the sun, something is. Approach from the right direction, trailing behind the planet's own motion around the sun, and the spacecraft leaves carrying a slice of that motion with it, more speed than it arrived with. Jupiter, in exchange, loses an infinitesimally small sliver of its own orbital momentum, too small to ever measure against a planet that size, but real. The same conservation law that governs any collision, just played out across empty space instead of a pool table. Most missions use that borrowed momentum to bend sideways, gaining speed within the plane the way a slingshot fires forward. Ulysses spent it climbing out of the plane instead, aiming the same borrowed push in a direction almost nobody had aimed it before. The rule from before does not vanish here. It just gets cheaper if you spend it in the right place. Plane changes are not equally expensive everywhere along an orbit. They cost the least where a spacecraft is moving the slowest, and the most where it is moving the fastest, because the cost scales directly with speed. Near Earth, a spacecraft carries the full 18.5 kilometers a second. The sun's pull demands at that distance. Out near Jupiter, roughly 5 times farther from the sun, a spacecraft coasts at only about 8 kilometers a second, less than half the sideways rush Earth carries. Slower orbit, cheaper turn. Do the comparison plainly. 8 is a little under half of 18.5. Cut the speed by more than half, and the same 90-degree turn no longer costs anywhere near what it would have cost back at Earth. Turning near Jupiter's distance costs dramatically less than turning near Earth's, and that is true even before any gravity assist gets added on top. Layer the two savings together. Slower speed, farther out. A precisely timed, precisely angled pass by a planet massive enough to bend a path that steeply. What was a maneuver no rocket could afford near Earth becomes, out at Jupiter's distance, a maneuver an actual spacecraft with a limited tank of fuel could realistically fly. That is the whole reason Ulysses spent years just traveling outward before the poles were ever in reach. The distance was not wasted time. It was where the price came down. Reach Jupiter first, let its gravity do the bending. And only then does the climb over the sun's poles become something an actual mission budget can pay for. No other mission has repeated what Ulysses did. Not from a lack of interest. Ulysses showed exactly how narrow that path is, and exactly what it costs to walk it, even taken at the cheapest possible point along the way. A more capable successor, one that could study the poles longer or from closer in, has been proposed more than once over the decades since Ulysses stopped transmitting. Every one of those proposals runs into the same wall Ulysses only barely climbed around. Different instruments, different orbits, same bill. For now, going up out of the plane remains a route travelled exactly once, by one spacecraft, borrowing a single planet's gravity to do what no engine built could do alone. It is a small, strange kind of victory, a mission that never fought the debt described a moment ago, only found the one place in the solar system where that debt came cheap enough to settle. Ulysses is not the whole story of what humanity has sent toward the edge of the solar system. It is the one exception, the single mission that paid the price a different way. Everything else humanity has sent outward, everything still crossing the dark toward interstellar space right now, took a very different road. 5 spacecraft are making that different crossing right now. Voyager 1, Voyager 2, Pioneer 10, Pioneer 11, and New Horizons are all actually leaving the solar system, past the outer planets, and out into the dark between the stars. Line them up next to Ulysses, and the contrast says almost everything on his own. Not one of them climbs dramatically above or below the ecliptic. All 5 stay close to the same flat plane this whole story keeps circling back to. Where do 5 spacecraft built for such different destinations end up sharing the same road? Every one of them, once you check the numbers, is still riding inside the disk. Voyager 1 comes closest to breaking that pattern, and even its exception proves the rule. On its final planetary encounter, a close flyby of Saturn's moon Titan in 1980, mission planners deliberately bent its path upward, trading away any future visit to Uranus and Neptune for that one close look. The bend was real. Voyager 1 now travels tilted about 35 degrees from the plane, an incline steep enough to rival the grade of the steepest ski runs, the black diamonds groomed right at the edge of what a skier can hold an edge on. But the angle did not arrive the way Ulysses arrived at its own. It built up slowly, over decades of outward coasting after Saturn, not in one sharp bend at a single planet. Not a climb, a drift. Years of drifting, not one decisive turn. Voyager 2 took the gentler version of the same choice. It stayed close enough to the plane to keep visiting planets, sweeping past Uranus and then Neptune before finally turning outward at a shallow angle, dipping only slightly below the ecliptic rather than away from it. Both Pioneers and New Horizons, once its work at Pluto was finished, follow the same pattern. Every one of these 5 is, in the deepest sense, still riding inside the disk. They are heading toward its outer edge, not climbing away from it. There is a reason planners keep making that same choice, and it is the same reason that made leaving the plane so expensive to begin with. Staying near the plane turns the inherited orbital speed from a liability into an asset. The same sideways motion that has to be cancelled to go up becomes free momentum the instant a spacecraft simply keeps moving with it instead of against it. Cancel nothing, and the debt never comes due. Staying near the plane also keeps every other planet within reach for a gravity assist, because nearly every planet orbits close to that same flat disk. Leave the plane, and most of that free help disappears along with it. The rule is the same rule Jupiter's distance made cheap for Ulysses, only running in reverse. A spacecraft that never asks for a turn out of the disk never has to pay the price a turn like that demands. Voyager 2 shows exactly how much that help is worth. In the late 1970s, Jupiter, Saturn, Uranus, and Neptune lined up in a configuration precise enough to let one spacecraft visit all 4 using a fraction of the fuel that 4 separate missions would have needed. Voyager 2 flew that route between 1979 and 1989, each planet handing its momentum onto the next like a relay. The alignment that made it possible happens only about once every 176 years, longer than anyone watching the launch could reasonably expect to see it come around twice, and even a gift that rare kept Voyager 2 close to the ecliptic for the entire trip. Every assist nudged it sideways, every assist nudged it outward, none of them nudged it up. Here is the part that seems backwards. The moment a mission leaves the plane, it loses access to almost every planet that could have helped it get anywhere. Most of them simply are not up there to use. Jupiter is really the only planet massive enough and positioned usefully enough to bend a path steeply out of the ecliptic at all. That is exactly why Ulysses routed through Jupiter and nowhere else, and why any future mission built to fly over the sun's poles will very likely have to do the same. The Saturn, Uranus, Neptune, all of them sit close enough to the disk that a spacecraft can only borrow sideways and outward speed from them. Never a real climb. Only one planet in the whole system offers the kind of bend Ulysses needed, and Voyager 2 was already using it for something else entirely. Both Voyagers still carry something built for a very different kind of journey. A golden record, a phonograph disc etched with sounds and images, and music meant to describe life on Earth, included on the outside chance either spacecraft is ever found by someone else out there among the stars. Not a message aimed up, out of the plane, toward some direction chosen for its strangeness. A message aimed outward, along the same flat road every other departing spacecraft was already taking. They are well past Pluto's orbit now, carrying that record through the outer dark, still shaped, decades later, by the same flat plane and the same borrowed planetary momentum that first sent them outward. So the great deep space missions were never quietly refusing to go up. Nothing in physics forbids it. What they refused was to trade away everything the plane offers in exchange for one maneuver that would cost more than escaping the solar system outright. Not a locked door, a very expensive one. Leaving the disk is less like hitting a wall and more like walking uphill against a current every other path happens to be flowing with. A current that carries you outward for free if you simply let it, and fights you at every step the moment you don't. Stay in the current. And the whole solar system seems to hand you momentum for nothing. Step out of it, and every one of those gifts disappears at once, leaving only the old bill behind. The one no chemical rocket has ever been able to pay in a single stroke. Staying in the plane was never the limit of what a spacecraft could do. It was the limit of what one could afford. Not every mission that wanted to climb was willing to accept that limit as final, and not every one of them tried to pay it all at once. If you cannot pay for the climb in a single stroke, you can pay for it slowly, a little more angle with every pass. That is exactly what the European Space Agency's solar orbiter set out to do. Launched in February 2020, it carries a more modest version of Ulysses's old goal, and it reaches for that goal a completely different way. Instead of one dramatic bend at Jupiter, Solar Orbiter climbs through a whole series of gravity assists at Venus, one flyby at a time, each one nudging its tilt a little higher above the ecliptic than before. Nudge by nudge, the angle grows. By the end of its main mission, Solar Orbiter is expected to reach an inclination in the mid-20s of a degree. In an extended phase, that could stretch into the low 30s. Not close to Ulysses's steep 80 degrees, but high enough for something Ulysses could never manage. Solar Orbiter carries cameras. Ulysses only carried instruments built to measure particles and magnetic fields, so despite flying higher over the sun's poles, it never returned a single picture of them. Solar Orbiter tilted far less steeply, is on track to send back the first clear images of the sun's poles ever taken. That matters because the poles are where some of the sun's strangest behavior originates. The tangled magnetic field lines thought to drive the 11-year solar cycle, seen edge on from every vantage point humanity has ever had. A modest climb, patiently earned, buys a view 6 decades of spaceflight never managed to collect. That contrast is the whole lesson of this section in miniature. Climbing out of the plane does not require one heroic leap. It can be earned gradually, encounter by encounter, trading years of patience for a plane change too expensive to buy any other way. And then there is the mirror problem. Not going up, but going down, straight toward the sun, and it turns out to be almost the same fight. NASA's Parker Solar Probe launched in August 2018, built to fly closer to the sun than anything before it. Eventually it would pass within about 3.8 million miles of the sun's surface, well inside Mercury's own orbit, close enough to fly directly through the sun's outer atmosphere, the corona, and sample it firsthand. You would think falling toward the sun should be the easy direction. Gravity is already pulling that way. Just let go and drop. Wait. A spacecraft launched from Earth carries far too much sideways velocity to simply fall inward. That same inherited speed, the roughly 18.5 kilometers a second that makes leaving the ecliptic so expensive, works just as hard against falling toward the sun. Cancelling sideways motion costs nearly the same, whether you are redirecting it upward, out of the plane, or downward into the corona. The direction changes, the bill does not. So Parker solved its version of the problem the same way Solar Orbiter solved its own, patiently, and without ever leaving the plane at all. 7 times over roughly 7 years, it swung past Venus, and each pass trimmed away a little more of that stubborn sideways speed, shrinking and tightening its orbit closer to the sun with every loop. 7 flybys, 7 small withdrawals from the same velocity debt, until what was once impossible in one attempt became merely a matter of enough patient attempts. Look at these 2 missions side by side and something clicks into place. Ulysses needed to escape the ecliptic entirely, climbing up and away by borrowing Jupiter's gravity. Parker needed to stay inside the ecliptic, but shed enormous sideways velocity to reach the corona, borrowing from Venus instead. 2 opposite destinations, up and down, neither one reachable by raw engine power alone, both solved by the same patient tool, aimed in opposite directions. Not brute force, borrowed momentum, spent slowly. It is worth sitting with how strange that pairing really is. The spacecraft built to climb the farthest above the plane, and the spacecraft built to dive the closest toward the sun, turn out to be solving the same equation, only with the sign flipped. Whatever destination lies at the far edge of what a spacecraft can reach, up past the disk, or down into the corona, the same rule is waiting there. Borrow momentum from a planet, and be patient about spending it. That pattern points somewhere. Chemical rockets are extraordinarily powerful, but only in short bursts, limited by how much propellant a spacecraft can physically carry. Electric propulsion works on a completely different premise. An ion engine produces a thrust often no stronger than the push of a piece of paper resting in your hand, but it can sustain that whisper of a push for months, even years, using a small fraction of the propellant a chemical rocket would need for the same total change in velocity. NASA's Dawn spacecraft is the proof this works at scale. Between 2007 and 2018, Dawn visited the asteroid Vesta and the dwarf planet Ceres, and along the way, its ion engine accumulated a total velocity change of more than 24,000 miles an hour. Achieving that directly with chemical propellant would have demanded an amount of fuel no spacecraft could reasonably carry. Dawn managed it by thrusting patiently, a little at a time, for most of the mission. Apply that same patience to a plane change, and something that once looked impossible starts to look merely slow. Instead of cancelling 18.5 kilometers a second in one violent burn, an ion-powered spacecraft could chip away at that same debt gradually, over years, using only a sliver of the propellant a direct attempt would need. A whisper of thrust, held for years, adding up to a climb no single burn could afford. No mission has yet tried a large plane change primarily on electric propulsion. The idea remains untested at that scale, a promising road rather than a proven one, and honesty requires saying so plainly. We do not yet know if it will work at the scale a true polar mission would need. But as ion engines mature, it stands as one of the more realistic paths to eventually carrying something farther out of the ecliptic than Ulysses or Solar Orbiter ever reached, without needing another rare and fortunate encounter with Jupiter. A future mission may not need a planet's help at all. It may only need time. The spacecraft at least has a way forward. Slow as it is, the harder adjustment happens somewhere else entirely, inside the people riding along with it. The harder adjustment is not mechanical. It is not a matter of stronger engines or more patient thrust, no gravity assist to borrow, no years of Venus flybys to lean on. It happens inside a skull, and it happens fast enough that most astronauts feel it within hours of reaching orbit. You would think a body could simply learn to do without weight. Get used to floating the way you got used to riding a bicycle, a skill picked up once and then never questioned again. That is not what happens. What actually breaks down in free fall is not a habit. It is an agreement, and agreements can be broken in ways habits cannot. Your sense of up and down was never a single sense. It is 3 separate systems, each reporting independently, each normally so certain of the same answer that you never notice. There are 3 voices instead of 1. The first is buried in your inner ear, the vestibular system, a cluster of small fluid-filled chambers lined with tiny hair cells. Gravity pulls on that fluid constantly, and the hair cells read the pull the way a level reads a bubble in a tube of liquid, reporting which way is down and how the head is moving through it. The second system is your eyes, watching the horizon, the floor, the walls, anything with a visible top and bottom, and checking that picture against what the inner ear is reporting. The third system, proprioception, is simply the body itself. Pressure receptors buried in the feet, the joints, the muscles, quietly logging where weight presses against you and from which direction. On Earth, all 3 report the same thing, over and over, thousands of times a day, without you ever asking them to. Feet feel the floor, eyes see the floor. The inner ear feels the downward pull of a floor that is always exactly where it should be. 3 independent witnesses, 1 verdict, stitched together by the brain into something that feels like a single, obvious sense. It is not obvious. It is a vote, taken constantly and unconsciously, the way 3 separate clocks in the same house might all agree on the time without ever being compared directly. On Earth, the vote is never close, but here's where it gets strange. Take away gravity, and the vote falls apart. The inner ear still detects motion, tumbling, drifting, the small rotations of a body in free fall, but it has lost the one signal that used to anchor all the others. A steady pull in one consistent direction. The feet report nothing, because nothing presses them against a surface. The eyes may see a flaw, painted onto a module wall by engineers who wanted the crew to have somewhere to look, but that picture is now doing all the work the other 2 systems used to share, and doing it alone. 3 systems that had agreed for an entire evolutionary history suddenly disagree. The result has a name. Space sickness. Not sickness from movement, but sickness from disagreement. The queasy static of a body being told 3 different things about which way is down and trusting none of them fully. Roughly half of all astronauts experience some version of it in their first 2 or 3 days aboard a spacecraft. It passes. The brain adapts the way it adapts to almost anything given enough repetition, by picking a winner. Faced with 3 witnesses and no way to reconcile them, it simply stops listening to 2 of them. It learns to trust the eyes almost completely, quietly demoting the confused, contradictory signal from the inner ear until that signal barely registers at all. Within days, most astronauts move through a station with no more disorientation than they would feel walking through a familiar house, reading a wall panel as floor and never questioning it again. That adaptation is so thorough, it reverses. Astronauts returning to Earth after long missions sometimes go through a mirrored version of the same sickness. A few dizzy, unsteady days while the inner ear, ignored for months, relearns that its signal matters again, that the pull it is reporting is now real and not noise to be filtered out. Here is what that means, said plainly. The floor never moved. The astronaut's sense of it did. Twice. Not a training gap, not a weak stomach, not anything a body could simply toughen its way past. It is the same conclusion this whole story keeps arriving at from a new direction, just found this time inside a person instead of out amongst the planets. The up you have relied on since before you could walk is not a fact about the universe. It is a running agreement between 3 separate biological systems, tuned across millions of years of evolution to operate in exactly one condition, standing on a large gravitating body with a steady, unbroken pull in one direction. No evolutionary pressure ever prepared the inner ear, the eyes, or the pressure receptors in your feet for a spacecraft. Remove the condition they were built for, and the systems do not simply fall quiet. They start arguing, and while they argue, up and down stop being meaningfully different from any other direction in the room. The spacecraft, at least, can be engineered around its version of this problem, patiently, a little at a time, borrowed momentum spent on a schedule. The body has no such schedule to work with. It only learns to stop listening to itself, one system at a time, and then has to learn to listen again the moment it comes home. That same fragile arrangement, it turns out, does not end at the walls of one skull. It does not end at the edge of the solar system either. The same fragile arrangement that breaks apart inside a single astronaut, 3 systems arguing over which way is down, describes something enormously larger too. The sun, the planets, the whole flat disk you have been learning to call home, is itself riding inside something bigger still, a wheel within a wheel. The larger wheel has its own plane, its own up, entirely separate from the one this story has been tracking since the very beginning. The entire solar system sits embedded in the disk of the Milky Way galaxy. It took the same basic shape gravity gave the sun's own planets. A huge cloud of gas collapsing under its own weight, spinning faster as it shrank, its edges ironed flat by the same kind of collisions that flattened the planets into their shared plane. The physics did not change, only the scale did. This cloud held enough gas and dust for hundreds of billions of stars instead of 8 planets. And the disk it built is wide enough that light needs tens of thousands of years to cross even a small piece of it. Whatever plane that disk settled into, billions of years before Earth existed, became the galaxy's own permanent up and down, the same way the sun's collapsing cloud once fixed the ecliptic. The sun sits inside one of the galaxy's spiral arms, a stretch called the Orion Arm, sometimes the local spur, well out from the crowded galactic core, in what amounts to a quiet suburb rather than the busy center of things. Roughly 26,000 light-years separate us from the center of the galaxy. Light leaving that center tonight would not reach Earth for 26,000 years, longer than the whole span of recorded human history. several times counted end to end. From inside that disk, looking along its plane, we see it as a dense, pale band stretched across the night sky, the same edge-on view of a flattened disk that ancient sky watchers unknowingly traced when they mapped the zodiac, projected here on a scale their instruments could never have measured. They were looking at the same shape twice, once nearby and once impossibly far, without ever knowing it. Here is where the ground shifts again. You might expect that once you finally escaped the solar system's plane, you would reach some final, settled up. You would not. The ecliptic, the very plane this whole story has measured up against, sits tilted roughly 60 degrees from the galaxy's own plane. Picture a door propped open most of the way, short of a full right angle swing, and that is close to the angle between the two disks. Not a gentle lean, almost sideways. Two separate disks, each flattened by its own collapse, each carrying its own up, stacked against each other at a steep, uncooperative angle, not aligned, not related at all, climb straight out of the solar system's plane, and you are not climbing toward the galaxy's up. You are cutting across it, at an angle no spacecraft has ever been built to manage on purpose. And the sun does not even sit still inside its own galactic plane. It drifts. Slowly it rises above the disk, slows, falls back through it, dips below, and rises again, tugged back each time by the combined gravity of everything else riding in that disk with it. Each swing carries the sun, and Earth with it, a few hundred light years above the plane, and then a few hundred below it. A distance so far past ordinary experience that no household object comes close. And yet, on the scale of the galaxy, it barely counts as a wobble. One full rise and fall takes roughly 30 million years. The sun's much wider lap around the galaxy's center, its full orbit, takes roughly 230 million years, informally a galactic year, so long that the last time the solar system completed one, the earliest dinosaurs had not yet appeared. Divide one figure into the other, and the sun rises and falls through its own galactic plane about 8 times over a single galactic year. 8 rises, 8 falls, all nested inside one much larger loop, and all of it too slow for a single human life, or a single human civilization, to notice happening at all. Some researchers have asked whether that slow vertical rhythm leaves any mark on Earth itself, whether drifting nearer the crowded galactic plane exposes the solar system to more interstellar material or cosmic radiation, with consequences for climate or even the long history of life here. It is a genuinely open question, and an old temptation, matching one slow cycle against another and hoping they explain each other. The mechanism, the sun rising and falling through its own galactic plane, is solid, well measured, not in doubt. The link to anything that happened on Earth is not. We don't yet have the evidence to say either way, and honest science leaves it there rather than forcing a connection the data does not support. Stack what you now know. Earth spins on an axis tilted about 23.4 degrees from its own orbital plane, roughly the recline of a lawn chair tipped back toward the sun. That orbital plane, the ecliptic, tilts a further 60 degrees against the galaxy's own plane. The galaxy's plane drifts, in turn, against even larger structures around it, and beyond the galaxy that structure gives way to more galaxies, clustered together, strung along filaments in a cosmic web, with no flat plane left at all. At every one of those scales, a local up exists. At every one of those scales, it has nothing to do with the up nested just inside it, or just outside it, each tilted by its own separate history, each one found on its own terms, often centuries apart from the rest. No single thread runs from your own 2 feet through the ecliptic and out to the galaxy's plane. Each link in that chain had to be measured on its own by different instruments, in different centuries, before anyone could even suspect the others existed. Escaping the solar system's plane, then, was never going to hand you some final, universal up. It only hands you off to a larger disk with a different answer, borrowed the same way the last one was, from whatever mass happens to dominate nearby. And even that borrowed answer runs out eventually, replaced by something wider still, on, with no floor to the stack and no ceiling either. Working out even the nearest of these, the one belonging to our own solar system, took longer than anyone would guess. And it did not start with a spacecraft. It started with people lying on their backs, watching the sky, long before anyone knew what they were actually looking at. No telescopes, no rockets, just eyes night after night, tracking the sun, the moon, and the handful of planets bright enough to follow without instruments. And slowly, across centuries, a strange pattern emerged. None of those lights wandered freely across the dome of stars the way you might expect if the heavens truly had no shape at all. The sun kept to one narrow band. So did the moon. So did every visible planet, always drifting through that same strip of sky, never straying far outside it. Season after season, generation after generation. Ancient sky watchers named that strip the zodiac, and built calendars, harvest cycles, festival dates, and navigation routes around its rhythm, tracking it faithfully for thousands of years without ever once seeing it from any angle but this one. They had no way to explain why the wanderers stayed inside one narrow lane instead of scattering across the whole sky the way the fixed stars seemed to promise was possible. They were looking straight at the edge of a disk, from a seat inside it, the same flat shape this whole story has been tracing since the beginning. Nobody watching knew that yet. Not a coincidence of the heavens. A perspective, and nothing more. That understanding did not arrive quickly. For most of recorded history, Earth sat fixed at the center of every model, with the sun, moon, and planets circling around it on nested spheres. The zodiac's narrow band was noted, measured, worked into elaborate systems, but never explained. It took the astronomers of the 1500s and 1600s to move the center of the picture, placing the sun in the middle and setting Earth in motion along with everything else. Once that shift was made, the planets stopped looking like they wandered on separate, unrelated paths and started looking like what they actually were, a family of orbits sharing almost exactly the same plane. The zodiac was not an odd coincidence of ancient sky watching. It was the disc's own edge, glimpsed from inside, exactly as it would have to look from a planet riding along it. But knowing the shape was not the same as knowing why it existed. Why would planets settle into one plane instead of scattering in every direction, the way loose debris usually does? That answer took another 2 centuries to work out. Only in the 1700s and 1800s did the physics catch up to the observation. Angular momentum, the same rotational memory that concentrates as a collapsing cloud, shrinks, forcing everything born from it into a single spinning sheet. The same mechanism traced earlier in this very story. The flatness was not decoration. It was not a preference of the planets. And it was not chance. It was a direct, unavoidable consequence of how the whole system had to form. What the eye had tracked for thousands of years as a narrow, mysterious band in the sky turned out to be the visible signature of physics working exactly as it must, centuries before anyone could prove it. Even that was still inference, a conclusion built from watching our own solar system and reasoning backward. Nobody had actually seen a disk form. Nobody had watched raw gas and dust flatten into planets anywhere else, only argued that it must have happened that way here because the math demanded it and nothing else fit. That confirmation did not come until space telescopes, in the final years of the last century and the early years of this one, turned toward young stars still wrapped in the material they were forming from, hoping to catch the process itself not just its aftermath. And there it was. Not theory anymore. Structure, glowing, photographed, undeniable. In 2014, radio telescopes captured one of the clearest images ever taken of a system still under construction. A young star called HL Tauri, roughly 450 light-years away. A distance no signal could cross within a single human lifetime. Not one lifetime, not several stacked end to end. Wrapped around that star was a wide, glowing disk of gas and dust, and cut into the disk were dark, concentric gaps, rings within rings, thought to be the tracks of planets still gathering themselves out of the surrounding material. The disk was flat, not roughly flat, flat the way our own solar system is flat. The same shape, the same physics, playing out around a star none of those ancient sky watchers ever imagined existed, circling a point in the sky they never once looked toward. Similar disks have turned up around other young stars since, each one another flattened ring of gas settling into the same pattern, as if the cloud had no other option once it started to spin and fall inward. So the zodiac was never a coincidence, and neither was the solar system's disk. What the earliest sky watchers traced without understanding, what the heliocentric astronomers finally placed in the right arrangement, what angular momentum eventually explained on paper, has now been watched happening in real time around other suns entirely, confirmed by light that left those young systems centuries before the telescopes built to catch it even existed. Flatness looks less like something peculiar to home, and more like the ordinary outcome of gravity and spin wherever a cloud is left alone long enough to collapse. It had taken thousands of years of patient watching, and 3 separate revolutions in understanding, each built on the last, to be sure of something that simple. And as settled as that certainty now felt, as universal as flatness now looked, the universe still had one more surprise waiting, a place where the pattern would not hold. That confidence held for every disk anyone had bothered to look for. But not every place that needed an up actually had one to borrow. Long stretches in orbit are not only a problem for spacecraft chasing an unlikely angle, they are a problem for the people who might someday live up there permanently, not on the moon or drifting past it, but staying in orbit itself, not passing through on a mission measured in months, but staying for years, building lives instead of running experiments. The free fall that lets ISS astronauts float weightless through their modules, the same free fall traced back at the very start of this story, was never meant to be a permanent home. It is already, quietly, doing damage. Extended time without weight costs the human body in ways daily treadmill sessions and resistance bands can slow, but never fully stop. Bone density drops, the same slow loss doctors see in patients confined to bed for months. Muscle mass drops with it, fastest in the legs and back, the muscles that spend a lifetime on Earth, fighting gravity and suddenly have nothing left to fight. Fluid that gravity normally pulls down toward the legs, pulls instead toward the head and chest, changing vision, sometimes for good. Astronauts manage these effects with rigorous exercise routines built into life aboard the station, hours spent strapped to treadmills and resistance machines that stand in for the weight the body has lost. Over months, that regimen mostly works. Over years, it does not fully hold the line. A body built for standing, walking and carrying its own weight against a steady downward pull does not adapt cleanly to carrying none at all. So if the solar system will not simply hand you an up wherever you happen to be floating, and exercise alone cannot buy back what weightlessness takes, the question becomes whether you can build an up instead. The answer engineers keep returning to is not more exercise, it is rotation. Spin a habitat slowly enough around a central axis, and something remarkable happens to the people riding inside its outer walls. They are pushed outward, gently, continuously, by what physicists call a centripetal effect, rather than gravity itself, but the body cannot tell the difference. Weight returns. Feet find a floor again. Inside a spinning station, up and down come back, but rearranged. Down becomes outward, toward the rim, where the push is strongest. Up becomes inward, toward the axis, where the spin barely moves anything at all, and the sensation of weight thins toward nothing. Walk from the rim toward the center of a rotating station, and you would feel yourself growing lighter with every step, the exact opposite of climbing a hill on Earth, where the higher you go, the heavier the climb feels. Near the axis itself, weight all but disappears. A small floating room at the center of a structure where every other room has a floor. Building it well is not trivial. Spin a small station too fast, and a crew member's head and feet, sitting at slightly different distances from the axis, feel noticeably different amounts of force, an uncomfortable mismatch called a gravity gradient, essentially a smaller cousin of the same physics that raises ocean tides. Stand up too quickly in a small, fast-spinning wheel, and the mismatch between your head and your feet can turn a simple motion into a wave of nausea. Build the wheel large enough and spin it slowly enough, and that gradient shrinks below what any inner ear could detect. Big and slow, beat small and fast. The habitat that feels most like Earth is the one spinning gently, at real size, not the cramped one whipping around fast to compensate. Here's where it gets strange. Nobody had to invent this idea recently. Engineers have been proposing almost exactly the same wheel for a full century, each generation rediscovering the same answer as if for the first time. In the 1920s, a Slovenian engineer named Herman Potočnik, writing under the pen name Herman Nordung, sketched a station shaped like a wheel, spinning slowly enough to generate weight along its rim, decades before any nation had a rocket that could reach orbit at all. In the 1950s, rocket engineer Werner von Braun picked up almost the identical shape, popularizing a wheel-shaped station roughly 250 feet across, about the length of a football field end to end, spinning to give a crew gravity while serving as a stepping stone toward the moon. His illustrations ran in magazines and on television, and that silhouette, a slowly turning wheel against black space, planted itself in the public imagination for decades. In the 1970s, physicist Gerard O'Neill pushed the same principle to an entirely different scale. Enormous rotating cylinders, miles long, spinning to hold Earth-like gravity along their inner surface, home to tens of thousands of people, with simulated weather, farmland, and daylight bounced in through mirrors running the length of the structure. His designs remain influential even now, still referenced by space agencies and private companies, sketching what the next generation of habitats might look like. 3 different eras, 3 different engineers, the same wheel, spinning for the same reason, and yet none of it is flown. Every station actually built and crewed, Skylab in the 1970s, then Mir, then the International Space Station, spins at essentially nothing, all of them free-falling rather than turning, not because the physics is in question. It has been understood since Nordung's sketches. The barrier is scale, the sheer volume of material a rotating habitat that size would require, likely mined from the moon or from asteroids rather than hauled up from Earth. A construction problem, not a scientific one. The drawings have been ready for 100 years. The engineering to build them at full size has not caught up yet. Underneath the wheels and the decades of drawings sits the same lesson this whole story keeps circling back to. Up was never something you had to travel toward. Earth's up came from gravity. The solar system's up came from the disk. A spinning station needs neither. It manufactures its own, out of nothing but geometry and motion, needing no planet, no star, no galaxy nearby at all. It only needs to be strong enough and steady enough for the body's own 3 systems, the inner ear, the eyes, the pressure in the feet, to agree on it the way they agree on Earth. Not a place, a force, built rather than found. Humanity has spent a century learning how to make an up out of thin air and momentum. Somewhere else, entirely unasked, nature had already found a stranger way to arrange one of its own. That arrangement was not manufactured. It was measured almost by accident, buried in the wobble of two small stars that were never the point of the study to begin with. For most of the history of astronomy, flatness looked like the rule everywhere, not just here. A collapsing, spinning cloud settles into a disk. That was the physics laid out already, and every young system image since, H.L. Tari among them, kept confirming it. Watch enough stars form, and the same flat pattern shows up again and again, planet after planet riding the same shared plane as its neighbours. The assumption held, our own solar system was, for most of the history, the only detailed example anyone had to check it against, and it kept checking out. Nobody had strong reason to doubt it. In 2025, that tidy picture got complicated. Astronomers working with the European Southern Observatory's Very Large Telescope in Chile have been studying a pair of brown dwarfs, objects too big to count as planets and too small to ever ignite the nuclear fusion that makes a star a star. They orbit each other closely, passing in front of one another as seen from Earth, an eclipsing binary, one blocking the other's light on a steady, readable rhythm. The team was refining that rhythm, tightening the measured orbit, doing the kind of careful bookkeeping that rarely makes headlines on its own. Then the numbers stopped adding up. Small wobbles kept showing in the pair's motion, wobbles the two brown dwarfs' own gravity could not explain between them. The team tested every ordinary explanation. Each one failed. Only one scenario fit what the data actually showed. A third body, a planet, tugging on both stars from somewhere outside their close embrace. Every earlier planet ever found orbiting a close binary pair had done the expected thing, riding in the same flat plane as its two hosts, exactly as the disk and collapse story predicts. This one did not. This planet, designated 2M1510 ABB, circles its two stars on a steep path nearly perpendicular to them, not tucked into their shared plane, directly above and below it, tracing a genuine polar orbit around a pair of stars, the first ever confirmed anywhere. The astronomers were not looking for this. Nothing in the original observing plan asked the question their instruments ended up answering. The planet only emerged because every simpler explanation for the wobble ran out, one after another, until the strangest one left standing turned out to be the true one. Scientists had floated the theoretical possibility of a polar circumbinary planet for years, in models and papers, without ever pointing to a confirmed real example. This was the first. The system sits about 20-some light years away, close by the standards of this whole story. The light reaching that telescope in Chile left the binary within a single human lifetime. Not before recorded history, not before the pyramids, just a couple of decades ago, practically next door in galactic terms. Here is why a planet 20 light years away belongs in a story about spacecraft struggling to leave our own solar system's plane. Every mission this exploration has followed so far, Ulysses bending itself over Jupiter, Solar Orbiter climbing slowly on repeated Venus passes, Parker diving the other direction toward the sun, has been fighting the same battle, cancelling an inherited sideways velocity just to travel a little way out of the plane it was born into. That fight costs more raw velocity than escaping the solar system outright. It has cost decades, one mission in more than 60 years, borrowed planetary gravity, years of patient flight time spent paying down a debt none of those spacecraft chose to owe. AIM 1510 ABB never had to fight any of that. It settled, or formed, into a stable orbit running straight over its two stars' poles. And it simply stays there, permanently, without spending a single unit of fuel to hold the line. No engines firing to cancel a sideways push it never carried. No gravity assist borrowed from a nearby giant. Somewhere in the galaxy, an entire world is living out, quietly and for free, the exact geometry that has cost humanity's space program more planning and more borrowed momentum than almost anything else it has ever attempted. That does not mean the physics was wrong. It means the physics was never the wall in the first place. Nothing about the laws of motion forbids a polar orbit. The only question was, ever cost? And this is what it looks like when nothing forces you to pay it. What makes a polar path expensive is not the destination. It is the starting speed, whatever sideways motion a body already carries the moment it tries to leave its plane. A spacecraft launched from Earth carries the sun's whole gravitational grip and Earth's own orbital speed built into it before the engines even fire. A planet that condensed into orbit under a different set of conditions, around a different pair of stars entirely, never picked up that same debt to begin with. It has nothing to cancel, so it pays nothing. Reachable somewhere, prohibitively expensive somewhere else. Same law, two completely different bills, depending only on where a body started and how fast it was already moving when it tried to leave. The rule that has shaped every mission in this story, that changing direction costs in proportion to the speed you already have, turns out to hold at the scale of a satellite and at the scale of an entire alien solar system, 20 light years off. It does not bend for distance. It does not care whether the plane in question belongs to a sun or to a pair of brown dwarfs eclipsing each other in the dark. And it was about to show up again. This time in places far closer to home than anyone watching the sky tonight might expect. Closer to home turns out to mean something almost embarrassingly literal. Right now, somewhere above your head, several satellites are doing exactly what took a spacecraft years and a Jupiter flyby to manage around the sun. They are going up. Not toward the sun's poles, toward Earth's. Weather satellites, many spy satellites, and a large share of the instruments mapping the planet's surface all choose polar orbits on purpose. Instead of circling the equator the way a communication satellite does, they cross almost directly over the north and south poles, one loop after another. Earth keeps turning underneath them as they pass. Give it a day, and a single satellite has scanned the entire planet in long overlapping strips. Something no equatorial satellite could ever manage from its fixed lane around the middle. Meteorologists track storm systems this way, strip by strip. Agencies watch ice sheets shrink and crops ripen the same patient, repeating way. It sounds like the same maneuver that took a Jupiter flyby to pull off around the sun. In a sense, it is. It just costs almost nothing. Scale is the whole difference. Earth's own spin at the equator carries you sideways at only about 0.29 kilometers a second, roughly the cruising speed of a jet airliner. Climbing into low Earth orbit takes about 4.9 kilometers a second, something like 14 times the speed of sound. Both numbers sound respectable on their own. Neither comes anywhere close to the 18.5 kilometers a second Earth carries around the sun every moment of every day. Cancel a jet's worth of sideways speed, and the fuel gauge barely moves. Cancel a planet's orbital speed, and the bill becomes the most expensive maneuver in the solar system. Put the two costs side by side, and the earlier numbers finally read as a match set. Ulysses spent years and a Jupiter flyby to buy roughly 26 kilometers a second of plane change near the sun. A polar orbit satellite buys almost the same 90-degree turn relative to Earth's own spin for a sliver of a single kilometer a second. Folded into the launch profile so quietly, nobody on the ground counts it as a separate expense. The maneuver has not gotten easier. The speed it has to fight has simply gotten smaller. Say the rule plainly, because this is where it finally locks into place for good. A plane change costs in proportion to how fast you are already moving inside the plane you are leaving. Close to Earth, moving slowly, the cost is a rounding error. Close to the Sun, moving at 18.5 kilometers a second, the very same maneuver can empty a mission's entire fuel budget. Same law, same geometry, a completely different price, decided only by your starting speed. Not a different rule for satellites. The same one, just paying a much smaller bill. The International Space Station lives inside that arithmetic too. It orbits at an inclination of about 51.6 degrees to Earth's equator, tilted just past the midpoint between lying flat and standing straight up. That angle was not chosen for the view. It was chosen so rockets launching from both American and Russian sites, at their own latitudes, could each reach the station without paying more than they had to. Even this close to home, an orbit's angle is never arbitrary. It is always a calculation, weighing cost against purpose. Here's a stranger consequence of that same tilted plane geometry, one most people have wondered about without ever being told the answer. If the moon circles Earth and Earth circles the sun, why isn't there a solar eclipse every single month? The moon's orbit is tilted too, about 5.1 degrees off the ecliptic. Stack roughly 10 full moons edge to edge, and you would cover that angle. Most months, when the moon passes between Earth and the sun, it passes a little high or a little low, missing the alignment by just enough to miss the shadow entirely. Only twice in each orbit does the moon's path actually cross the ecliptic, at 2 points called the ascending node and the descending node. Only if the moon happens to be new or full at nearly the same moment it crosses one of those 2 points does an eclipse happen at all. Ancient astronomers charted the pattern for centuries before anyone understood the geometry behind it, noticing only that eclipses returned in a repeating cycle a little over 18 years apart. Without knowing, they were simply timing 2 tilted circles, meeting at the same 2 points, again and again. New moon at a node, a solar eclipse, full moon at a node, a lunar eclipse. Every other month, the moon simply passes by, unremarked. Not a monthly event, despite the geometry looking like it should be. A twice-a-year alignment, precisely timed, called an eclipse season. A few degrees of tilt is the entire difference between routine and rare. Saturn carries the same lesson somewhere you can actually watch it happen. Its rings sit directly in the plane of the planet's own equator, tilted about 26.7 degrees from Saturn's path around the Sun. As Saturn crawls through its orbit, a trip of about 29.5 years, long enough for a child watching through a first telescope to reach their late 20s before the planet completes one lap, that fixed tilt slowly changes how the rings look from Earth. Early telescope observers sometimes reported the rings gone entirely, convinced for a moment they had vanished for good, before they widened back into view years later, wide open and dazzling for years, then narrowing. Then, roughly every 15 years, about the span between a child's birth and their last year of school, the rings turn edge onto our line of sight. Not a solid structure from every angle, a blade when you catch it edge on. Shrink Saturn's rings down to the width of a football field, and they would be thinner than a sheet of paper. Broadside, they look like the most solid object in the solar system. Edge on, they very nearly disappear from view. That is the same trick seen twice now, once in the Zodiac's edge-on band traced by ancient sky watchers, and once in Saturn's vanishing rings. A flat structure looks completely different depending on where you happen to be standing when you look at it. None of this is a set of separate stories. The satellites overhead, the station's tilted orbit, the moon's near misses, the rings turning to a blade, they are the same rule, showing up at a different scale each time. A flat rotating structure stays flat only because something forced it flat, and moving away from that flatness always costs something, whether it is a satellite's slightly pricier launch or an entire spacecraft, borrowing a giant planet's gravity just to bend a few dozen degrees off course. The price changes from one scale to the next. The rule underneath it never does. And there was still one more place that same rule had been written into the sky all along, in plain sight, for anyone who knew when and where to look up. That place was closer than any spacecraft ever travelled. You do not need a mission to see the disk. You do not even need a telescope. Stand somewhere far enough from any city, under a sky dark enough to show every star, just after sunset or just before sunrise, and a faint band of light rises tilted from the horizon. Astronomers call it zodiacal light. It runs along the same narrow strip the ancient sky watchers traced across the zodiac, the very edge of the disk this whole story has been circling since the first section. That light is not starlight. It is not sunlight scattering through the air the way a sunset does. It is sunlight reflecting off dust, countless tiny grains left behind by asteroid collisions and comets slowly falling apart as they pass near the sun. That dust drifts thin across the inner solar system, but it piles up thickest in exactly one place, the same flat plane every planet already orbits in. Confine the dust to a plane, and the light it reflects has to trace that plane too. A narrow, tilted column instead of a general glow overhead. Some cultures mistook it for something else entirely. They called it a false dawn, a soft light before the actual sunrise, easy to confuse with morning arriving early. Nobody explained what it really was until the 1800s and 1900s, when astronomers finally traced that pale glow back to sunlight, scattering off interplanetary dust. Stand under a dark enough sky tonight and watch that column rise, and you're looking straight along the plane of the solar system. No equation required, no spacecraft needed, not a diagram, not an abstraction sealed inside a textbook. A real glow, rising over the horizon on every clear night, whether anyone bothers to look up or not. Everyone already knows one guide star. Polaris sits almost directly above Earth's North Pole, on the extension of the planet's own spin axis, which is why it barely seems to move while the rest of the sky wheels slowly around it. Sailors steered by it for centuries. Every culture with a night sky worth watching built stories around it. That reliability turns out to be a coincidence of timing. Earth's axis wobbles, tracing a slow circle over roughly 26,000 years, longer than agriculture has existed on this planet. Polaris has not always marked the pole, and it will not always mark it. Someday another star will take its place, and a different one after that. The solar system's own up, the direction standing perpendicular to the disk every planet shares, has no such marker. Look for the north ecliptic pole and you find only the faint, forgettable constellation Draco. No bright star sits there. No shape sailors ever fixed a course by. Nothing woven into any culture's myths the way Polaris was woven into nearly all of them. The south ecliptic pole fares no better, buried in Dorado, the swordfish, visible only from below the equator and just as unremarkable. Not marked, not remembered, not steered by, not once, in all of human history. A patch of sky that matters only on paper, defined by calculation rather than any beacon burning inside it. And there is a reason nobody ever needed to name that patch of sky. Nothing goes there, no planet orbits toward it, no asteroid belt drifts in that direction. Head straight for the north ecliptic pole, and you leave behind the planets, the asteroid belt, the Kuiper belt, nearly all of the flattened dust that makes the zodiacal light glow, arriving eventually at a view no spacecraft has ever actually earned. The whole disk, laid out flat beneath you like a record spinning under a raised needle. Ulysses came closest of anything humanity has ever built, and even Ulysses only reached a little past 80 degrees, short of the full 90 that view would require. Meanwhile, the plane itself stays crowded. The asteroid belt between Mars and Jupiter holds the overwhelming majority of everything ever catalogued out there, almost all of it within a few degrees of the ecliptic. Jupiter's Trojan asteroids sit trapped in gravitational pockets 60 degrees ahead of and behind the planet, still almost exactly in that same plane. Short-period comets loop back from the Kuiper belt on schedules astronomers can predict years in advance, and they too stay close to the ecliptic. Every one of these is free material, encountered simply by staying where a spacecraft already needs to be for efficient propulsion. Climb toward the pole instead, and all of it gets traded away for a view of nothing. Zoom out far enough, past the galaxy's own disk, and even that trade stops mattering. Our galaxy is one of dozens crowded into the local group, dominated by the Milky Way and its slightly larger neighbor, Andromeda. The local group itself is a small corner of something vastly bigger, the Laniakea supercluster, a name that means immense heaven in Hawaiian. Mapped only within the last decade or so, Laniakea holds roughly 100,000 galaxies. Light needs more than 500 million years just to cross it end to end, longer than complex animal life has existed on land. At that scale, galaxies stop scattering at random and start tracing a shape of their own, long filaments strung with clusters, connected at dense nodes, separated by voids nearly empty of anything at all. Scientists call it the cosmic web, and somewhere past even that pattern sits a stranger finding still. On the very largest scales, the universe looks almost exactly the same in every direction, a property astronomers call isotropy. The faint afterglow left over from the universe's earliest moments, released about 380,000 years after everything began, has been mapped down to a precision of a few parts in 100,000 across the entire sky, the equivalent of measuring every wall of a room and finding them the same temperature to within a fraction too small for any ordinary thermometer to register. No center, no edge, no preferred direction anywhere. Somewhere between the tilt of a planet's axis and the whole of everything, the very idea of up simply stops applying. Back near our own sun, the story of up is still unfinished. Engineers keep sketching a more capable successor to Ulysses, one built to finally carry cameras and photograph the sun's poles directly, something Ulysses itself never could. Every design runs into the same wall. Chemical rockets are not getting meaningfully more efficient, and the 18.5 kilometers a second of inherited velocity is not getting any cheaper to cancel. What is improving, slowly, is low thrust propulsion. Ion engines refined further, solar sails maturing past experiments, each one chipping away a little more cheaply at that same old bill. Someday, perhaps decades from now, some spacecraft may finally climb higher than Ulysses ever did. Until then, a machine launched in 1990 still holds the record for going up, which brings the whole question back to where it started. Right now, wherever you are, you know exactly which way is up. You feel it without having to check. In the chair beneath you, in the floor under your feet, in the quiet certainty that never once asks to be questioned. That certainty feels absolute, like a fact stitched into the universe itself. It is not. It is a temporary agreement, negotiated between your body and the nearest large mass, Earth, valid for exactly as long as you stay close enough for its gravity to win. Travel far enough, and it dissolves, first into the directionless drift of free fall, then, if you go far and fast enough, into an entirely different up, the one defined by the disk every planet, asteroid, and comet in this solar system already respects. An up so expensive that in over 60 years of spaceflight, only one machine has ever seriously chased it. Standing on Earth, up is borrowed from the planet under your feet. Standing somewhere in the depths of the solar system, up is borrowed from the disk itself. Standing on a planet like 2M1510 ABB, 20-some light years away, Circling 2 stars at once from a polar orbit no chemistry could ever buy, up would mean something else again. Not a universal fact. Not something the universe hands down equally to every corner of itself. A local gift, borrowed, and only for as long as you stay within reach of whoever lent it to you. None of that makes the up you feel right now any less real. If anything, it makes it rarer. It took a cloud collapsing exactly as it did, a disk flattening under its own spin, a planet condensing in exactly the right orbit, a moon forming large enough to hold that planet's tilt steady, billions of years of exact sequence, just so you could stand up out of a chair without a moment's thought about which way to go. Up, down, every direction you have ever trusted without asking. All of it borrowed, never owned,